right, welcome. Hello, hello. How you guys doing? Got a full class this time. So you may or may not know, my name is Sam Snow. I have a brother named John, so Jon Snow he kind of knows nothing though. If you have any knowledge of Game of Thrones, you'll get that joke. I just need to become the president of something, then I can be President Snow, like the Hunger Games villain, right? So welcome. I'm going to teach you about water and wastewater treatment. So water is kind of my thing, and it's even in my name, right? Just in the cold form. All right. So today I'd like to get to know you a little bit. And normally, in the past, I had used a website called Kahoot, but now they want to charge me an arm and a leg just to survey a few people. So all the quiz participation material I had there, it's now limited to like, oh, you can't do that, and you can only do 40 people if you did. So I'm trying something new today. So I'm gonna have you test with me a poll, and I'm sorry I haven't had a chance to test it yet. It's taken me a while to try to find something. We could get 40 of you to participate in the Kahoot thing if we need to, but just something to liven up and say hello. Here's where you're coming from. You know, how long you've been in your major, what major. Most of you will be civil engineers. You'll probably have a few chemical engineers that are here to learn about the water treatment side of things. And there may be some people from elsewhere. So that's kind of the type of things I want to hear from you about. So if you don't mind being a little bit patient with me, I'll try that with you in a couple minutes. But just a couple quick things, and I'll tell you a little bit about myself along the way with that. So today, I'm just going to tell you about the course in general, what we're going to do, how it's going to go, what kind of resources you'll have. We'll take a look through Moodle. I've got it mostly set up now as of kind of late last night, and walk you through what to expect for the class. We'll go through the syllabus, and we'll probably even just touch on some of the basics of water and wastewater treatment today, kind of if we get there. So that's kind of my plan today. Any of you were you particularly excited to be here? Let me poll the civil engineers first. Any civil engineers that were like actually excited to take the class? Okay, great. I understand most of you, like, it's just required and you just have to be here. So just giving that context, there's some chemical engineers, this is optional, so probably you're excited to be here, kind of interested, like what's this going to be about? So I'm going to lay out some expectations for everybody. One thing we've done in our environmental engineering department, the EVEG, we've separated the EVEG students from this class so that they can go a little more advanced. They have more of the background here. So some of the chemical engineers, I'll just tell you right now, it's probably cool if you like show up in a week. Today will be helpful, but we're going to go through the next week some fundamentals of chemistry because some of these guys haven't had it since high school. Some basics about mass balances. How do we even approach something like this that most of the chemical engineers probably have been doing for some time? So if you'd like the more basic approach and refresher, great. By all means, stay here and participate. But just a little warning, the first week, I need to catch some people up. And my intent is not to get stuck on that side of things so that we can actually go and learn some about water and wastewater treatment. But I do want to use these types of tools. So that's kind of where we're at. That's the deal. So real quick, we'll just go ahead and start. Well, what is environmental engineering about? And kind of what is it about water and wastewater treatment what is the technical approach? It's almost all about mass transfer or transformation. And that means we're going to do things called mass balances because we can't create or destroy matter. There's occasions where maybe bacteria will be growing. Of course, we can maybe use that to consume some waste. That's the wastewater side of things. But in general, we can track the mass or the number of something as a function of time. And when we put this in some sort of a reactor to make things happen, that's what we're using to accomplish a goal. So a really, really highly technical way to say this is we have some stuff in some other stuff, and what we want to do is send it through some sort of reaction so we have a lot less of that stuff, and maybe a little pile of that other stuff. We've separated it, okay? All the stuff. Now, I'm just kind of being silly there, but that actually summarizes pretty well most of what environmental engineering does. We deal with, let's say in our class, water or wastewater. There's maybe some contaminant in it or something that we don't want there, and we're going to send it through a process so that we can separate or destroy, transform. Maybe we're oxidizing bacteria with chlorine to the point where they're no longer living, and the bacteria cells are still kind of hanging around in there, but they've been destroyed. They're no longer able to reproduce. So we've taken the number of living bacteria that could infect somebody close to zero, or close enough to zero. So we've just done a transformation, or perhaps we are doing a filtration, and we are blocking the bacteria from even passing through a membrane filter and removing them that way. So one way or the other, this could apply to air treatment, this could apply to treating groundwater contamination. All sorts of environmental engineering is kind of summarized in that way. Of course, there's more complicated things to it sometimes, but what we are interested in for this class is understanding how do we model this process in the middle. Can we put a number on that? Can we put a rate on that? Can we understand what we need to do in order to achieve a particular percentage reduction or a particular outcome below a threshold so we can ensure that the water is safe? Perhaps we need to protect a receiving water from the waste stream. So how do we know that the waste water is not going to pull down the oxygen too much and kill all the fish, right? All of these pieces are going to go into understanding how that transformation is happening, and how do we know whether or not it's enough transformation to do our purpose. So all of this is conservation of mass, essentially, or sometimes we will have conservation of number if we're talking about something like a bacteria and we're trying to inactivate or destroy them. So we'll talk a lot about the rate of change of stuff. So we'll be talking about rates of change, and that's going to be some mass or maybe number over time. Usually we will talk about that in the context of some volume. So very often we will have, in a volume, we would multiply by that volume, and that's going to be essentially a concentration per time. So we'll see very often maybe a change in concentration per change in time. You've seen derivatives like this all over the place in calculus and stuff, right? So very often we'll be talking about a mass per time change in some volume. So mass over volume is concentration. And we'll go through all of this carefully so you know what notation I'm talking about. So we could consider how much chlorine might be remaining in my water bottle. I filled it up, this morning at some point, and there was probably some chlorine remaining from the disinfection, the treatment plant. Comes through the pipes. There's a little bit of residual there, and now it's been sitting in here. It is slowly decaying. I could use a rate constant to model and figure out at what time will this reach zero chlorine remaining, right? If I know where it's at now, I know something about how quickly it's changing over time. I could put that in and find a number and say, oh, I'll probably be no more chlorine left in X number of hours if I had that kind of information. So that's the type of thing we're going to be dealing with and applying it to different sectors of water treatment, and then giving you a good picture of what does drinking water treatment look like, what does wastewater treatment look like. I know on our little flow chart, it says wastewater treatment. So a lot of you think this is the wastewater class. Well, actually, we're going to do both, and a lot of the class will start with the drinking water specific kind of stuff. That's also more of my specialty. I have worked with research and otherwise with wastewater and drinking water. But drinking water is sort of my specialty, and a lot of the processes will overlap. In fact, we disinfect wastewater also frequently. So a disinfection process that I'm teaching in the context of the drinking water process is also applicable to our wastewater. Sedimentation is another good example. We're going to use gravity to remove some stuff. And when we do that, we're actually going to apply that to both drinking and wastewater treatment typically. So a lot of the class will kind of be applicable to both. But as we go through the syllabus in a minute, you'll see the theme is going to go from drinking water to wastewater. And in fact, it'll be a little bit of a theme like physical to chemical to biological treatment. We don't really use biological treatment for drinking water typically, trying to get rid of anything biological. And so that's going to take us from mostly drinking water, but also somewhat wastewater, into mostly just wastewater. That's kind of the scope of the class, and we'll see that in a few minutes. Okay, so I'm going to try this poll. I'm not sure exactly what's going to happen, like I said, so I appreciate your patience here. What I'm going to have you do is take a look, go to this link on a phone or a laptop, pull that up, and it should bring you to a page that looks a little bit like this. Okay, I'm going to go ahead and start the poll. See what this does. And I'll take the poll with you here. I'm hoping we can get live results. That's my goal here, is to kind of see how many of which majors we have. While we do that, while you get that set up and find that spot, I'll tell you a little bit about myself. So I went to school at Georgia Tech, grew up outside of Atlanta. Kind of made sense that Georgia has something similar to the top scholarship. It's the Hope Scholarship there, and so I wanted to go somewhere to get that, and ended up there and just stayed there for grad school as well. So my undergraduate program was actually not engineering. It was Earth and Atmospheric Science. It's kind of a very technical environmental science type of program. I actually, since they were teaching a lot of meteorologists, I also had to take thermodynamics and calculus 3 differential equations, all sorts of stuff. So I was pretty well prepared for engineering, but then I switched into engineering for grad school. All right, how many of you have gotten there? Good. All right, I'm gonna continue. Let's see if we get some live results. Okay. Hopefully, okay, here we go. All right. And let me know if you need that link again. All right, so we have 49 civils, 3 EVEGs that snuck in. I think you're supposed to, if you are in EVEG, I think you're supposed to take the other section. Talk to Dr. Pardue about that. Sometimes there might be a way if there's a timing issue. I'm just not sure. 12 chemical engineers, and who's the other? What do we have?
Biological engineering.
Okay, great. Yeah, so occasionally we have some bioengineers. So, any particular interests? Just kind of neat class. Okay, great. All right. So next question is, how many years have you been at LSU? I've been here 8 years now, since 2016. All right, looks like we've got pretty much everybody. 63. Yeah, okay, we're still counting. So mostly seniors, a few juniors, and a few others. We have like super seniors. Is that others? Nice. Nothing wrong with that. In fact, actually, that was where I went to school. That was so common. It was like almost uncommon if you're done in 4 years. So, no problems there. Okay. Then, how old are you? And you don't have to give me the exact. Just a range here. Of course, I'm in the 24 plus. I just turned 37 this year. So still a millennial, but starting to show some age, getting there. Young enough to live stream this to YouTube, by the way, so that's something else I was going to tell you about. We are currently live, so you'll have access to this lecture later. Okay, so most of you, pretty typical. I mean, it kind of follows the previous question, right? So most of you are. Did I even vote? Yeah, I did. There we go. There we go. 2 of us are 24 or over. Okay, where are you from? And by that, I mean kind of where did you spend most of your childhood? Oops, sorry. And from Georgia, I'm just barely 3 states away, so I guess I'm somewhere else. Okay, about 54 of you from around here. 7 of you pretty close, and then 1 international, and 1 other that is at least as far as Georgia, which doesn't feel that far. I lived in Michigan for 2 years, which definitely felt a lot different. And Louisiana is a different South than Georgia, but it's still the South. It's not that different. Michigan was a very cold and a very very different place. Okay. Next, out of the topics that I kind of mentioned, which are you least comfortable with? I'm supposed to answer this one because I should be, but you can answer however you see fit. All right, we got 4 of you. Well, yeah, there we go. Now 4 of you who don't even need the class. Great. You guys want to give some lectures? Always good to see. Okay, so only 26 as chemistry. Actually, in the past, I didn't have biology as a separate tag, so it's good to know I added it this time. With biology, it's actually not too much true biology. We're actually looking at it kind of in a numbers perspective for a biological system. So you don't have to know a whole lot of biology there. For the chemistry, I'm able to keep it relatively basic and catch you up on stuff. So you should be able to handle it. There will be a bit of pH stuff that you're just going to have to work through and hopefully master. But I'm happy to work with you on that, and I will give you some good review on that. And this class isn't all about chemistry, but you really probably should know how does chemistry affect chlorination. There are some important concepts there. The pH will change what kind of chlorine we have, and we need to do some calculations to that, because if the pH changes a little bit, that changes quite a bit of our system. Okay, so the next one, I'm going to have you look at a picture in our PowerPoint. Let's do this. And just take a moment and think about that. Think about what you see, and select your favored answer. This is probably the only question I really needed to know to see about your knowledge of chemistry here. Pretty easy, because if you're just frustrated by looking at it, you can just hit like I hate chemistry, right? So none of that. Okay, so I'm going to select that maybe I've seen one of those in the state fair. So the joke is it's a Ferris wheel, and the chemistry nerds might get that because iron in the 2+ state is ferrous, is how we call it. 3+ is ferric, so it's a ferrous. Kind of like a Ferris wheel, but spelled different. And of course, it's also not chemically possible. So that's definitely a solid choice. I understand for the 25 of you who selected iron oxide, there's iron in there. Good on you. And there was an oxygen. Yep, there's iron and there's oxygen. So So a good guess, but yeah, and 14 of you just gave up. So six was that 8 of you recognized and thought you were really smart and like that's not a thing. But some of you liked the pun, so that's good or got it. In fact, it's funny that the way I remember ferric versus ferrous, because it's easy to forget, is some time ago one of my sisters got me a T-shirt that had basically that on it, Fe2+, and from then on I always remembered ferrous is that Fe2+. Okay, so the most important question: do you like a good pun? Well, I don't hear too much groaning, so that's a good sign. All right. So plenty of time to enjoy that, and let's see. Okay, chemistry jokes are the thing today. All right. Even the one where you don't like it, I made you make a pun, so there. Okay, I think that's about it. Thank you for doing that, and I'm glad that it basically worked well enough. All right. While I'm here, let's go ahead and talk for a minute about our Moodle page. So if you go to Moodle, you'll see something that looks a little bit like this. I've got the syllabus posted here. If I have any updates to that, I'll make a note. I'll let you know if it's something important, and I'll kind of let you know when it was updated. So that'll be a great resource for you. We all say that to you and point you to it, but really, if you have some basic question, it's there. It'll be there right for you. Another resource you'll have is a document here that will show you all of the, I'm just not gonna do that right now, all of the formulas and tables you'll have on your exam. Okay, and I'll update this to include a few more for your second exam, and for the final exam, you'll have even a few more. So I'll just open that document from here so you can take a look at what is included there. Just this here. Okay. So on every exam, you'll have the periodic table. You're going to have a density lookup table, it's got basically the water density and dynamic viscosity is typically what we'll use. So I'll talk a little more about that in the future, but you'll have those as resources, and then some list of formulas that I think you ought to have these at hand and know how to use them. So it's on you to study these to know what each parameter means and where it's coming from, what it's doing in this equation, and how to apply that to a problem. I don't care so much that you memorize the equation, but I do encourage you to study them so that you know, right? Because I want you to be able to use them for the problems. So here we have a few. They're relatively simple. This is my current plan for you to use on the first exam. Okay, so that'll be there on Moodle. There are a list of practice problems referring to the book that I'll talk about when I show the syllabus next. So you could take a look if you wanted more particular practice with a particular subject matter. You can go there and see which problems I'm recommending. I'm going to update this link and make it live for you so you'll see it later. If we go to YouTube, let's do that here. We could actually see the channel and live right now. So I just have this channel, and we could even pull this up and watch, and it's a bit of a YouTube inception, right? All right, enough of that. Okay. So that'll be there. That'll be, I'll put all of these, all the lectures that I'm posting there. We'll go into one, essentially one group or one playlist for this class. And so we'll kind of have a reference material for class here. Now, already kind of talking ahead of myself a little bit, but for the sake of the class, obviously if I'm lecturing live and you could watch it later, you don't have a whole lot of incentive to be here necessarily. I strongly encourage you to be here and participate. You'll see in the syllabus I have some participation credit. That's a good way that I can award you for being here and present enough for me to get to know you, to have a class where it's not just me lecturing nobody. If that's going to happen, then we'll do a lot of in-class participation assignments. Okay? I hope not to need to do that or feel the need to do that. And I like to give you some flexibility if you did have something come up and you had to miss, and to give you lectures online as a tool to help study, right? So what I actually care about here is that you learn. That's my job, and that's what my aim is to grade you on, is how much did you learn. So that's my aim, and you know, if I feel like I'm not doing, like you're learning less because I put this stuff online, I'm going to try to encourage you to make better use of the class time you're paying for, essentially. So that's kind of the way I look at it. All right, so the rest of the Moodle page, you'll see I'll place assignments here. I've got plenty that are loaded and hidden right now. We'll talk a little more about that, and I'll post them as we go. Some quizzes I will post here. Again, I used to use the Kahoot thing, and I could get actual 8, 9 numbers and put those into Excel and all that. Not doing that anymore, so I will be doing some participation quizzes on Moodle. Maybe it'll be the case that I say in class, hey, we'll have a quiz on this topic. Make sure to do this in the next 24 hours. Okay? That might be one way I do it, or I might say, all right, within this week, you know, tackle this assignment here. I'll have you read a couple things along the way. I'm giving a special lecture on Flint water crisis, and there's a required reading on the cryptosporidium outbreak that 30 years ago. It's a pretty big one in the world of water treatment. So I'll have you read a couple things and do a participation that way. That's generally where your participation score is going to come from. Of course, I also reserve the right to adjust that based on my interactions with you either way. Okay, after that, everything else is basically the course content. Next time, we'll really get into more of the units, mass balance, reaction kind of stuff. Maybe I'll touch on it, pull that lecture open for a few minutes today, and then I'll post those slides here. I will try to post the blank ones here in case you want to follow along, and then I'll upload later the ones that I've written on. So if I come back to my slides here and I make some notes, you'll have those notes on there for you. All right, so I think that's about it. If I do something like an exam recap where I go through solutions to exam materials, I'm not going to post that publicly on the YouTube page, but I'll give you a direct link that you could use, and I would put that probably in this introduction section where we have some sort of a exam recap. Okay. All right, so let's take a look then at the syllabus. Now that I've kind of said it all already. Okay, we are here today at this time, yep. Also, you can go to this link, already showed you. That's where it'll be. Office hours, I'm aiming to hold every Monday at 11 to noon, essentially. That'll kind of be a standing time. You're welcome to come by. We can also meet over Zoom if needed, or you can make an appointment with me. So all of those are opportunities for you. Please make use of it if you'd like to. The textbook, I do recommend getting it, or maybe getting one copy within a group of friends or something. You'll see we'll go through probably about 3 chapters, and I'll expand a little bit on there. The textbook itself is a nice introduction to environmental science and engineering more broadly, and then we focus in on a few parts of it, which is kind of a nice thing because the problems are a bit more accessible in terms of they don't go way, way deep into the chemistry or way, way deep into the reactor design. Now, we'll talk about, oh yeah, this certain chemical principle could make an impact, or what about the dead space in this reactor that could make an impact, but we're just not going to go at that depth. So it kind of helps keep us at a higher level. It's very readable. I actually used it when I was a student, and that was part of the reason I selected it for this class. But if you do want to go a little deeper, there are some other resources here. Some of these are free online with the LSU library. So if you need any extra materials, or if you're just wanting some extra materials, take a look there. To me, they're not quite as useful in terms of teaching or reading and understanding, just because the way they've been written just doesn't quite do it like this one. So I think you can do fine without the textbook if you really wanted to, but if you're finding the topic interesting or want a decent reference that's accessible, it's readily usable, I would encourage you to get it or considering getting it. Okay, objectives for this class are pretty simple, pretty straightforward. We're going to be working on design tasks for water and wastewater treatment and learning the fundamentals of what we need to do that. Okay, there's a few specific examples, and we'll cover these topics. So we'll see that all when we go through the kind of tentative schedule too. Grading, my plan is to have 3 exams. That includes the final exam, each of those equally weighted, and then homework and class participation together make the weight of 1 exam. One of the things I've done here is in the past I would have homework be counted a little bit more, but I found, especially with posting things online myself, I was spending too much energy trying to make sure that students that were doing a good job on the homework and not using any resources they found online that were solving the problems for them, they were getting their grades punished compared to the students who were just cheating and using the resources. So I've changed my policy on homework, and simply I'm not grading them for correctness. That's going to be up to you to monitor your own level of correctness and challenge yourself in terms of how well are you engaging with these problems? Are you doing a good job? Are you learning how to get them correct and struggling through that? That puts more responsibility on you, but I think that's preferable than me trying to make new problems every time for every homework. It really takes too much time, and it works better if I do that simply for the exams instead. So those will be for completion. That might be a nice thing to hear, but keep in mind that is a challenge for you to make sure that you're using them well to learn. So those homeworks will be, I'm certain you can find them, the solution somewhere, but I'm also certain you don't need to. Just give it a shot, use it as a way to study, and submit completed homework, and that'll be the best case. And we will also go through the solutions and talk about them, answer questions, and all that. So really, I hope that you don't have any incentive to go look elsewhere, because you can just get it all here, and it doesn't matter anyway. Okay, we already talked about participation. I don't think I will use that new poll, quick poll thing, or whatever it was called, direct poll, to collect attendance, because I don't think that has a functionality. So instead, it's going to be on you to be participating, attending, and engaging with whatever quizzes in class or take home that I post. All right, I will use Moodle to post things, and we'll expect you to upload your assignments there. I will try to make sure that I announce due dates and things like that, but definitely see Moodle and rely on that as well, because it should be there for you. Okay, so then the class material. Today, of course, is an intro. Then we're going to get into kind of a primer on units, mass balance kind of stuff. How do reactions work? What is a reaction? How does that differ from a chemical reaction? And could they be the same thing? And then get into a chemistry refresher. So like I told you, for the chemical engineers, maybe the first week and a half is pretty boring, and you probably don't have to be here. I'm going to leave that up to you. Typically, the drop add date is somewhere around here, so I wouldn't take attendance anyway, because it's hard to keep track if people are dropping and adding. I just want to let that all go by, and so I'm going to leave you completely up to you, your discretion as to whether or not you need that stuff. Then September 10th, then we get into Intro to Drinking Water specifically. And that'll take us really into the core course material, where I expect everybody will be hopefully learning something new. And from there, we'll start with the physical processes first that we use for water treatment. We quickly edge into chemistry with coagulation here, and that is a chemical method we use to facilitate the physical method. So it's going to start merging and being multiple topics in one. But for the most part, exam one will primarily be physical stuff and checking on that the chemistry refresher worked and that you can apply that to the relevant coagulation stuff. From there, we're going to go into a little bit more of the physical processes, but quickly shift into chemical as we go from filtration into disinfection processes. And if we have time, we might do some advanced oxidation stuff along with that, and have a lecture on the Flint water crisis. There's a chance I might rearrange that, the order based on where we get to, but I'm going to do my best not to change these exams. So if you see the date and you see a very big concern today, now's a good time to talk to me about it, or this week, so that I can run it by the entire class before everybody gets everything scheduled and expected and makes their study plan. So I'm open to hear from you, but if it's 1 week out and you realize you have 3 exams that day, I'm sorry. It's going to happen sometimes, and that's tough. I'm not going to change it a week out. If we have some major event that closes campus or something, maybe then we would adapt. But okay, from there, the rest of the class, starting around in November, would really be wastewater more strictly. Of course, a lot of this is both. We'll deal with some of the regulations. I worked briefly as a permit writer for the NPDES, which is the National Pollutant Discharge Elimination System, while I was in Michigan. And so I have some pretty good context there to share with you. How do we regulate it? Kind of what are the fundamental motivations for regulating our wastewater? What are the types of things we consider? And then we'll cover the basics of wastewater treatment, and also understanding to what extent does the treatment impact rivers or streams, lakes downstream. Okay, so with that, then we would have Thanksgiving break, a bit more on that nutrient removal, recycle side of things, an exam review, and then the final exam. This is the correct date as of yesterday. Occasionally, LSU changes things, so we'll be monitoring, but this is what I expect to be our final exam date. Okay, any questions? Issues so far? Right. So one other thing, just so you know, I'll be teaching 2 classes this semester, and this will be the second one right after I teach another one. So at some point, my voice might give out a bit, especially early in the semester when I'm just not used to it. So please be patient with me if that happens. But I'll do my best. And do let me know if I'm not speaking loud enough or something at any time. I'm not wearing this microphone for anything in the room, so I'm hopefully relying on just my voice for you to hear me. This is for the recording. All right. Okay, so let's give it a quick overview then about water and wastewater treatment. We'll end early today, but I just want to give you a few things here. So really, we can categorize water and wastewater treatment separately in terms of how we regulate and what motivates our treatment. And really, the treatment that we need is going to inform what kind of treatment we use, right? If you imagine for a moment living on the space station, what do you do with your wastewater? You ever thought about that? You can't bring new water up there because it's extraordinarily expensive. It would probably cost millions of dollars to bring this one bottle of water, right? So you're not ever going to get rid of the water, hopefully. You need to conserve that mass. So they have a very interesting conservation of mass problem in the space station. The water that's there, they want to be able to reuse completely. So any wastewater that's produced needs to be extracted. The water itself, the H2O, needs to be extracted, and everything else needs to be transformed into something that could be maybe ejected or perhaps in some other way recycled, right? I'm not actually sure what they would do with the remainder. But most of the waste that we excrete, most of that is water by mass anyway. So depending on where we're at and what we need to use the water for will dictate what level of treatment we need. So for drinking water treatment, we have both health and aesthetic standards. So how many of you like to drink brown water? Anybody? Nobody. Nobody likes to drink brown water? Are you sure? By show of hands, how many of you have had Coke, tea, or coffee today? Oh, so some of you do like drinking brown water. Okay. Aesthetic standards are interesting because they don't necessarily correlate to health. Now, perhaps the amount of sugar in those drinks might be a health hazard, but we drink tea, we make brown water, and then we drink it on purpose, and we like to. Of course, we don't want it coming out of the tap water because we know something must be wrong, right? And it feels right that we would reject that. Fair enough. And so we have aesthetic standards that would include color and taste and odor, even though it's technically possible to have some very bad flavors that are not at all bad for you. Hydrogen sulfide is a good example. Well, if you have a lot of it, it's very, very bad for you. But the amounts we can detect, if you've had well water that smells like rotten eggs, at the level we can smell it and it smells or maybe tastes bad, it's actually probably fine. At some point, it would be too much, but it's often the case where people have that in their groundwater. It smells gross. They don't like it aesthetically, but health-wise, it's fine. So there are cases of that. So the aesthetic standards are not mandatory. These are recommendations. We only want it to be brown if we specifically asked for it to be brown with, Coke, Dr. Pepper, whatever, right? Any standards here for health-related things, these are required or enforceable by law through the EPA. So typically the EPA will say, all right, here are the standards. We're going to delegate responsibility to monitor each of these to each state, and then you'll have a state Department of Environmental Quality or something similar who then makes sure that your drinking water treatment, your public municipalities are meeting some thresholds, meeting some standards. So if you have a private well, you probably don't have anybody monitoring that, but hopefully you would have had it checked when you started extracting water and perhaps periodically thereafter. So there's a difference there. It's possible to have a private well that doesn't have good water, but nobody knows it. That's certainly much more possible than having a public water source that should be being checked frequently. Of course, we'll talk about some examples where that did not happen properly. Wastewater treatment, typically we motivate it based on what intended use are we going to use the water that's receiving the wastewater. So if we are discharging wastewater into the Mississippi River, that is a bit different than discharging it into a crystal clear stream flowing in the mountains, right? We typically want to make sure that our discharge is not going to impact the local biology in any way where it could harm what we call intended uses, which would include fishing and recreation, boating, perhaps use it as a water supply, or simply the ability to support the local ecology. So there are some watersheds and some bodies of water that are designated as like high risk and very, very pristine. Some in northern Michigan, for example, where maybe you have a wastewater discharge, but you have to clean it up quite a lot. Whereas when you're discharging to the Mississippi here in Baton Rouge, it would be difficult to make an impact on the Mississippi and the ecology there at this point. There's just simply so much water, so much in the water already from all the runoff, that the biology there, it's not particularly vulnerable to the relatively small changes. Of course, we are still going to treat to some standards, but for example, our South Baton Rouge wastewater treatment plant, normally you would chlorinate to disinfect and then you would dechlorinate, so you don't have an impact. The chlorine is hazardous to an extent to the receiving water. Well, in that case, there's actually no need to dechlorinate because of the scale of the Mississippi, so they don't, and that's what permit they have. So depending on what's going on, that's how you treat. One of the more obvious ones we'll talk about is rivers should not be flammable. There have been cases of that, and you can imagine a grease fire on top of, like if you have an oil slick, grease fire on a river. How do you fight that? All this water, and what happens when you throw water on a grease fire? It just sprays the flaming grease everywhere, and it's not good. All right, so I guess I'm a little backwards here with my slides. This is the front cover of the textbook that I'm recommending. I think we've talked about basically all of that, the other stuff already. All right, I think that's probably good enough for today. We'll get into the units, mass balance, and maybe even chemistry refresher next time.